Good afternoon, I guess it is, folks. Already at this wonderful Lindau meeting, we have had some excellent examples of science that advanced very quickly. Perhaps a laboratory discovery or perhaps a clever idea which led in a very short number of years to deeper understanding, perhaps even to practical applications. In the next minutes, though, I would like to lead you through an example of a very different scenario. Sometimes it simply doesn't happen that way for various reasons, and things happen very much more slowly. So I want to tell you a story of an example of science that did advance so slowly that the important details were unfolding over a period of 100 years, and the rapid advances perhaps are beginning around about now. So let me get the buttons going here. So here's an overview of the sort of highlights of things that happened during this 100-plus years. Starting in the early years of the 20th century, of course, Einstein's relativity theory, first the special theory in 1905, and the general theory, including accelerations and gravitation, 10 years later. A few years after that, one of the first predictions of relativity, that starlight should be bent when it passes a massive object such as the sun, was more or less confirmed in an experiment which wasn't very accurate, but which at least appeared to give confirmatory results. And basically that made Einstein famous overnight, and it showed that a new and more complete understanding of gravitation was at hand. One of the more or less immediate consequences, for theoretical physics at least, was that it appeared that these equations formulating Einstein's relativity theory had wave-like solutions. So the question arises, do gravitational waves exist? Something analogous to electromagnetic waves, but involving the gravitational force. Anyway, there were arguments about that I'm going to lead you through over several decades. But progress was extremely slow, not least because there were no experiments. And it looked as though at that time that there might never be experiments. Around about 1960, Joseph Weber got interested in the possibility of experimental detection of gravitational waves, and I will mention just a few words about that as part of the story. Completely by accident, as far as this story is concerned, pulsars were discovered in 1967. Rapidly rotating, strongly magnetized neutron stars out in space in our own galaxy. And these turn out to have a part in this story. I should mention that, and a few years later, a pulsar orbiting around another dense object, probably another neutron star, was discovered, and that was the work in 1974, which led to my own honor of being invited to Stockholm some years later. You will see as we go how this work 45 years ago now, a long time back, is involved, but quite by accident. It was certainly not what we were intending to do when the experiment leading to that discovery was started. There is an interesting theoretical controversy that arose, which I will refer to as the quadrupole formula controversy, and I'll explain a little bit about what that was about, and that was part of what led to the additional progress that we'll get to. Interestingly, the items on this list, and finally there's the reception of gravitational waves that you'll hear about in much more detail in the next lecture by Ray Weiss. The items on here with an asterisk and highlighted in red are all connected to a Nobel Prize, and that's of some interest. Over all of this time, things were happening slowly, but they were obviously important physics for one reason or another. It was a complicated and tortuous path, as I described it, but it was nevertheless an unfolding scientific story. So the field equations of general relativity appear to have wave-like solutions, but questions arise as to whether these solutions are physically meaningful. Are they really describing waves that exist and that, in principle, are at least are subjectable to experimental testing? Are the waves independent of the coordinate system? That's an important consideration, and was very much in the mode of discussion that was taking place during the 1920s, 1930s, whenever some work was being done in this area. And I might mention that this was quite a this is the time of the rise of quantum physics. This was quite a backwater of physics in many ways during most of these years. Is it true that the that the waves that appear to be solutions of Einstein's equations are a necessary consequence of the theory? Can we calculate the speed and the energy being transported by these waves, and so forth and so on? Finally, leading to the question, could these waves possibly be detectable? Just for interest, I have written down here direct quotations taken from papers written at the time about the possible existence of gravitational waves. There are no gravitational waves. Plain gravitational waves traveling along the positive x-axis and so forth can be found. Gravitational waves don't exist. It turns out the published literature at the time, scant though it was all over the place on this question. And interestingly, every one of those quotations is taken by a paper, taken from a paper written by Einstein himself. So we didn't know the extent to which these things might be or might not be particularly significant. Just a few more comments about the state of affairs during the times. Two papers by Einstein in 1916 and 1918 were the first ones that actually attempted to deal with the wave-like solutions. The 1916 paper had some of the essentials written down. There were a few mistakes in the paper, and a couple of years later, some of those mistakes were cleared up. And in particular, this quadrupole formula that will arise again later in my story, first appears in that 1918 paper. It is essentially a paper in which he's not doing a formally rigorous calculation based on the field equations, but he's using analogies to electromagnetism and so forth. But in any case, it appears that he's taking the possibility of gravitational waves very seriously, and he recognizes at that time that quite possibly these waves are beyond our capability of detecting ever. The coefficients in the equations are so small that the waves are extremely weak, and this is going to be a difficult experimental problem, maybe impossible. Eddington, Arthur Eddington, the British astrophysicist, did a linearized computation that was suitable for weak field, slow motion conditions in which he developed the nature of the waves significantly further. And in answer to the question, do gravitational waves exist in general relativity, Eddington said definitely yes. A few years later, in the 1930s, now Einstein by this time has moved from Europe to Princeton, and in 1936, he was working together with a young associate, Nathan Rosen, in which they put together a paper in which they reached the conclusion, no, that these gravitational waves that appear to be solutions of the equations are not physically real. However, as you will see, there was a controversy about the paper itself, and as it turned out, the referee of the paper pointed out some mistakes, and I want to lead you through that story because it's quite interesting. And this his piece of physics history was unearthed by a man named Kennefick, Dan Kennefick at the University of Arkansas. He's a distinguished physicist himself, but he's put most of his effort recently into history of physics. In a book called Traveling at the Speed of Thought, published by Princeton University Press in 2007, Kennefick describes this story. he finds in the Einstein papers a letter that Einstein wrote to his friend Max Born in May of 1936, in which he said, "Together with a young collaborator, that's Nathan Rosen, I have arrived at the interesting result that gravitational waves do not exist, though they had been assumed certainty to the first approximation." Well, so Einstein and Rosen wrote up this work and submitted it to the American physics journal, the Physical Review. At that time, an up-and-coming journal. It was not yet, I think, the distinguished repository of physics papers that it became later. But part of the effort that was going on at the time was to raise the standards of this paper, and they took the task of reviewing submitted papers very seriously. Anyway, Einstein and Rosen had answered the question by saying, no, these waves do not really exist. Here is John Tate at the time, the young editor of the Physical Review in 1936. It appears from the history that he and his colleagues in the Physical Review office probably puzzled over this paper for a week or two, maybe 3 weeks, before doing anything else. And finally they decided, we've got to send this out to someone else who can figure out what's going on and get it right. And so he sends the paper to a mathematical physicist, Howard Robertson, who was in the mathematics department at my university at Princeton at the time. And Robertson comes back with a letter to Tate dated July 14th, 1936. So here I'm going to read you a few sentences from the letter from Tate, from Robertson to Tate. He says, "Dear Tate, well, this is a job. If Einstein and Rosen can establish their case, this would constitute a most important criticism of the general theory of relativity. But I have gone over the whole thing with a fine-tooth comb, mainly for the sake of my own soul, and I can't for the life of me see that they have established it." And then he goes on to explain what he finds wrong. He says, "I have written up in duplicate a series of comments which you can, if you are so minded, send to the authors. The alternative would be to publish the paper as it stands, taking account only of my comments A and B on page 1, which deal with typographical errors of a minor sort." Okay, then he goes on to more important flaws that he sees in this paper. Such a paper would be certain to give rise to a lot of work in this field of gravitational waves, which might be a good thing, provided they didn't flood you out of house and home with more papers. If you decide to refer it back to the authors with my comments, please send them the copy written on white paper, keeping the yellow paper copy for your files. Okay, so this is the standard process of reviewing that at least is taking place in the Physical Review at the time. But Einstein is not used to this. It did not happen that way in European journals at the time. Anyway, Tate writes back to Einstein and says, "I would be glad to have your reaction to the various comments and criticisms the referee has made." And here is the response of Einstein to Tate. You can't read it. I can't read it anyway either. But he is clearly handwritten a letter back to the editor in which he says, translated into English, "Mr. Rosen and I had sent you our manuscript for publication, and we had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. On the basis of this incident, I prefer to publish the paper elsewhere." So Einstein pulls the paper, and in fact, I believe it is the fact that he never published in Physical Review after this time. All right, so he's annoyed. But it turns out when Robertson wrote the referee's comment, he was actually on leave, and he was at Caltech at the time. He came back to Princeton in the meantime, and in private conversations with Einstein, in which he did not review that he had written the referee's report, he convinced Einstein that he got it wrong in various places. And a few months later, I think it's 7 months later, in February here's Robertson, by the way. In February of 1937, Robertson writes another letter to John Tate, editor of Physical Review, in which he said, "You neglected to keep me informed of the paper submitted last summer by your most distinguished contributor, but I shall nevertheless let you in on the subsequent history. It was sent without even the correction of the 1 or 2 numerical slips pointed out by your referee to another journal. And when it came back in galley proofs, it was completely revised because I had been able to convince him in the meantime that it proved the opposite of what he thought." So, okay, we all make mistakes, and we don't necessarily get everything right the first time. Here's Einstein in 1937 in his office at the Institute for Advanced Study in Princeton. He's probably thinking over Robertson's comments. I don't know. And here is the note added in proof to the paper as it actually appeared in the Journal of the Franklin Institute in 1937. He says, "Note, the second part of this paper was considerably altered by me after the departure of Mr. Rosen for Russia, since we had originally interpreted our formula results erroneously. I wish to thank my colleague, Professor Robertson, for his friendly assistance in the clarification of our original error." Okay, so at this point, I guess we have Einstein and Rosen end up saying, well, maybe gravitational waves can exist after all. This, of course, is the time when Europe is descending into what becomes the Second War, and physics is not happening very much in the late 30s and for the next decade and plus. There's a famous, well-known to gravitational physics people at least, meeting that took place in Chapel Hill, North Carolina in 1957, in which some of the heroes were Dick Feynman, Herman Bondi, Ivor Robertson, Felix Pirani. Basically, Feynman and Bondi had a very interesting thought experiment, which essentially proves that gravitational waves are a necessary consequence of general relativity. If you think of a rigid rod with a couple of beads on it, the beads can slide on the rod, and the gravitational waves come by. The beads are going to want to move a little bit as the gravitational potential changes, and those beads will have friction with the rod. The rod will also want to expand and contract a little bit, but because it has internal electromagnetic forces to hold it relatively rigid, it will distort less than the beads want to move, and therefore there will be friction as the beads move. That friction is energy. So not only do these waves exist and will cause these things to happen, they must carry energy with them. If general relativity is correct, gravitational waves must exist. And Bondi, Pirani, and Robertson went on to publish a few papers. So there's just the title of paper 3 in their series, which was a very important one that showed these things must necessarily be true. Well, just to show there are Feynman, Bondi, Robertson, and Pirani. So shift gears here a minute. I've going on. Nuclear physics is making progress during these years as well. The neutron was discovered in 1932 by Chadwick. Almost right away, a couple of astronomers, Walter Baade and Fritz Zwicky, recognized that this understanding might well explain the nature of exploding stars known as supernovae. And they say in a brief paper, they wrote, "With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a new form of star, the neutron star, the end point of stellar evolution." Within a few more years after that, Oppenheimer and his student Volkoff had published a paper with the internal structure of a neutron star roughly worked out. It depends on the equation of state of nuclear matter and bulk, which is not known with precision even today, but we're doing better with it as time passes. But in any case, we had the basic understanding that this very dense form of matter might exist. By 1962, Riccardo Giacconi and colleagues discovered cosmic X-ray sources, which were interpreted as possibly being specific examples of neutron stars, which turned out to be correct. But even more importantly, in 1967, the first pulsar was discovered. And within a fairly short time, these objects were correctly identified as rapidly rotating, strongly magnetized neutron stars. A spinning flywheel in space with very little external influence makes a very good clock. The spinning magnet generates radio noise, which can be detectable over interstellar distances. That's how they're detected with radio telescopes. And we had a whole new tool, a whole new type of cosmic object to use. A number of us sent out, as it happened, I had just turned in my PhD thesis in January of 1968. So I was looking for something new to work on. I was staying on at the Harvard College Observatory as a postdoc and was more or less able to work on whatever I wanted, and decided this would be fun. I'm going to go observe these objects, these pulsars. Within a few months, we had found another one, and others had also started searches looking for these objects. And they turned out to be fascinating objects with important consequences for much of astrophysics. But we had not any idea at the time that they were also going to be important for understanding gravitational waves. In 1972, I started with then my graduate student, Russell Hulse, at the University of Massachusetts on a pulsar survey of the sky, looking for more of these objects. We had in mind identifying enough of these neutron star objects to determine what their distribution throughout our galaxy was like, so that we could compare them to the distribution of other types of stars and see how they fit into the general scheme of stellar evolution. We were going to use the giant radio telescope in Puerto Rico, a 1,000-foot, 300-meter spherical cap attached to the ground, over which is a feed antenna which can be moved up here to steer the telescope within about 20 degrees of the local zenith. Here's an up-close photograph of the focal arrangement. Here is Russell Hulse, who shared the Nobel Prize in 1993 with me, as a student in 1974, keying in the bootloader to what at that time was called a mini computer, something about the size of a refrigerator. And you can see the dated equipment there. Just a little more history. Russell's project was extremely successful. He found dozens of new pulsars, 50 in the end. But in 1974, we had found 40 new ones, and most importantly, one of them turns out to be orbiting around another object. We can tell that because the ticks of its clock are Doppler shifted. So the velocities change over the course of time, and the Doppler shift repeats every 7 hours, 45 and something minutes, a little less than 8 hours, over a highly non-sinusoidal curve that you can see there. That particular graph with the handwritten sketches was made at the time of the discovery. So right away, this told us that this object is in a tight orbit around another massive object, moving in an eccentric elliptical orbit, a fascinating system. Still, we were not thinking about relativity. A few details here about the object itself. I think I'd better move on, but right away, when we started publishing some of the details, even by word of mouth, people recognized that this orbit should gradually lose energy in the form of gravitational waves, if general relativity is correct. And that should cause the orbit to shrink, and that it might, in principle, be measurable. So what about it? We did the calculations to see whether this might be possible, and it turns out that the size of the orbit is something like 10 to the 6 kilometers. That's the scale. 10 to the 9 meters, if you like. And the amount of energy loss should cause this orbit to shrink by about 1 millimeter per orbit. 1 part in 10 to the 12 per orbit, more or less. Astonishing, and surely beyond our capability to measure. This thing is 25,000 light years away, halfway across our galaxy. But it turned out, no, it's not necessarily impossible to measure, and that's what we set out to do. By this time, Russell Hulse had finished his thesis and was off to do another job, and in fact, he moved back into a different field of physics in which he busied himself for many years thereafter. I think I should say a few words about this quadrupole formula controversy coming to an end, because it seemed that we were going to be able to measure, to actually have some experimental data. It was really important to find out what the theory really says. And at that time, there was still some doubt about whether sufficient mathematical rigor had been used to calculate the rate of change of the orbital size that we were using. Some of these questions were again addressed by Feynman, by some of his colleagues at Caltech, Peters and Matthews and others. There was a vigorous debate still underway, but that eventually started to go away as the data improved and drove more and more people to carefully look at the derivation of the phenomena that we were observing. So I'm going to show you a sequence of slides here in which time is on the horizontal axis, starting in 1974, and on the vertical axis, we're plotting the advance of the phase of the orbit that is in excess to what there would be if the orbital period, and therefore size, remained absolutely constant. So it looks, even after a few years, as if things are starting to change a little bit, and after a few more years, it's starting to get more and more clear, and after more years, it's getting more and more, almost 10 seconds now after about 10 years, and it continues to get bigger. And those measurements basically motivated additional theoretical work, which essentially showed that the quadrupole formula indeed gives the correct result for a orbiting pair of self-gravitating objects like this, and that in fact it is applicable to binary star systems like the orbiting pulsar that we were observing. Most of these observations over these years were done by me together with a colleague, Joel Weisberg, who's recently retired from Carleton College in Northfield, Minnesota. So here is what the curve looked like, I think, here's what it looks like just a few years ago. The total, notice that in the previous one, we were down to what, a total of 14 seconds of additional orbital phase, and now we're down to well over a minute. It's a big effect that accumulates quadratically over time, and that's one of the reasons why it was an experiment well worth following, even for several decades. But the results unfolded slowly. Okay, well, just a few comments at the end about gravitational wave detection. Here's Joe Weber in his lab in the 1960s. Here's a piece in the New York Times science section in 1990 where they were starting to talk about what you're going to hear about in the next lecture, the big instrument known as LIGO. And I think one of the reasons that the National Science Foundation in the United States was, in the end, willing to take the fairly large risks involved in funding the massive project that became LIGO was that we now had real sources. We really understood sources that, in principle, should be detectable with an instrument like LIGO. So, as you know, in February of 2016, the world became aware that LIGO had succeeded, had found a pair of black holes coalescing into one another, and that led to another Nobel Prize, as you're well aware. So let me just summarize by saying a few morals of the story. Experiment and theory are very important. If there's no experiments, it's hard to make theoretical progress, and that's one of the reasons why this took so long. Nothing is obvious at first, even if you can write down the equations. And even Einstein wasn't sure whether these waves were going to be real or not. You should do calculations, even if you need to approximate the results. Nonlinear equations like those of relativity are difficult to manage, but you can make approximations. You should expect the unexpected. There are going to be some blind alleys along the way. And for sure, if you smell something interesting, you should follow your nose. Thank you all very much.